So you know how we can actually read words even if they're misspelled, if they still have kind of the same shape, usually the same amount of letters, but maybe an L is switched with an H, and there's sort of a scrambling, but there's still sort of a pattern, like almost like a hieroglyphic. There's a shape to words, and we can pick that up even when they're totally misspelled. Well, that's what these researchers are calling a phenomenon called typoglycemia. But now imagine an artificial intelligence that can do that same thing, but to like a whole nother superhuman level. And that's GPT-4 for you. Researchers at the University of Tokyo decided to find out just how good is GPT-4 at the word jumble game. So they created something called Scramble Bench, which is like a giant playground which can test how well big large language models can actually unscramble a sentence, and then unscramble the sentence into the question that it should be and figure out how well it can interpret the answer. And even though we're probably all numb to how many breakthroughs we have with AI, it might still surprise you to know that GPT-4 was nearly perfect with this. Why did I find this so surprising? And I think it's because, for better or worse, I have this idea of tokens, words being in sort of a latent space and measuring distance between them. And I thought the system would probably be pretty fragile. Like if it didn't find the word and it couldn't like locate it in the embedding along the feature line that it corresponds to, then how can the output ever be the answer to a meaningful question if it's all just based on distance? I would assume the system would be a little bit fragile around the edges that way, but I'm clearly wrong. The researchers took a whole bunch of different sentences and questions and turned it into essentially like an alphabet soup. I mean, they were the same length in words, but they were scrambled up in a way that was nonsensical. It's like giving somebody a puzzle that's all mixed up and seeing how fast they can put it back together and how accurately they can reconstruct the original. And at least for GPT-4, it can put these sentences back together with a 95% accuracy rating, even when the letters are completely mixed up. And this is super surprising to me. At least in theory, it seems like by messing up the letters, you're completely changing the way that it inputs the sentence. So what it translates it to shouldn't be a realistic answer. How does it know? Because it's not translating from language to language, even if you consider all sorts of different data types languages. It's just scrambled, so it shouldn't even be something that it learned the patterns of in the first place, at least the way I kind of imagine the system's working. I can even imagine something like text to MRI, but MRI is a data source that has a pattern in it, a feature that can be learned over time, so it seems like it could translate right, but we're actually talking about changing what you put into the system in a way that it didn't learn on the internet. If you took the entire internet, all that training data, it would have all sorts of misspellings in it, but it wouldn't actually have true jumbled up random words. It's like finding out somebody can read a book even when the words are dancing around the page. How? How do they do it? They're sort of unsettling to me because when there's not an explanation like that, I'm like, did something emerge or maybe I just don't understand it? I can imagine a system that learns all sorts of very rare errors. But how did it learn to quote unnatural errors? I think this challenges the way a lot of us understand how large language models work, and there should be some more research or some better explanations for how this could be possible. Poor speller, just being honest, GPT-4 often gets it right. But I expected my errors to be somewhat like other people's errors. But now I feel like GPT-4 has this ability to interpret these unnaturally scrambled words, and it was maybe something that we didn't know when it was first launched. That's one of the weirdest things, is when we release a model like this and we don't really understand its full capabilities, and it takes a lot of user testing and playing around and research to be like, oh, it can actually do these things we didn't know. And obviously if you put something out there that has capabilities you're not aware of, that can be dangerous because people can exploit those and use them for things that you don't know that they can and you're not totally prepared for. So now let me give you some context for the other way, because I've been trying to think through like, why is it that I really thought this wasn't going to be possible? And it reminded me of a paper that I read a little while ago called The Reversal Curse. So I brought that back to the forefront, did some research. Let me break that down for you. So this research paper that came out back in September was called The Reversal Curse. LLMs trained on A is B fail to learn B is A. Picture this, you're training a large language model, GPT-4, that A is the same as B. And it's just a variable, it could be anything you want, like taking a picture of an orange from just two different angles. A is pixels are a little bit different, but it's the same thing. So once you're confident that the model has learned that, you would think that if it can go from A and be like, oh, that's the same as this other photo, it could go the other way. You'd show it the photo and it'd be like, oh, I've seen this other angle of an orange, it must be the same as that other angle. But it doesn't always work that way. And this is what researchers are calling the reversal curse. From the research paper, they taught GPT-4 that this guy named Olaf was the 9th chancellor of Germany. So why did it draw a blank when it was asked the same question in reverse? Who was the 9th chancellor of Germany? Should be Olaf, right? You'd think if you learned it, but you just can't answer it. Like imagine a human who's just like bugs out. It wouldn't happen. Like telling your friend about a great new coffee shop that's down the road and to the left, and then when you ask them, where's that coffee shop located? They're like, oh, I don't know, I can't do it in reverse. No, if you visualize and understand where something is, you understand where it is. And the question can be asked in various ways. You understand the concept of where it's located. But of course, that's how a human brain works. But I always talk about how LLMs are basically similar to us. Like the perceptron and the neuron are kind of the same mechanism. We sort of have these approximating function, kind of input-output things. Why isn't this working the way you'd think it would? Imagine you ask the question to Gemini or ChatGPT, who is the mother of Ed Witten? Now that question is significantly trickier for a large language model answer than who is Taylor Swift's mother. Now, if you don't know Ed Witten, he's famous in a sense. He's an author, he's out on the internet, there's plenty of written by him, but he's a physicist, and he's not even nearly on the same level of volume and connection and fan base as Taylor Swift. In the world of neural networks, some bits of information like Taylor Swift are bustling cities of examples and connections and volume. I'm sure you've met a Swiftie. They're just like type, 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 and all of that got poured into Gemini and ChatGPT. So if Taylor Swift's this like bustling city, Ed Witten is kind of like this rarely visited village. It's on the map. There's plenty of connections to get there, but it's not gonna be like New York. It's gonna be more just like a little town or something. So when the question has somebody like Ed Witten in it, you're basically starting from a little village. You don't have as many ways to get out of the city in terms of the way the connections go throughout the large language model. And if you don't have a map and you're just gonna kind of like explore randomly, a big city gives you a million more ways that you can leave the city and end up with the answer of Taylor Swift's mother. Whereas if you're starting in a little Ed Witten town or village, there's just not as many roads out to go find his mom. And that's a little bit why A sometimes can equal B, but B doesn't always equal C. Going from Ed Witten to Taylor Swift is a lot harder than going from Taylor Swift to Ed Witten because there's so many more connections in that big city. So is it really a reversal curse, or is it just how large language models and neural networks work? To find out, these researchers decided to play detective and they conducted their own experiment. They trained the system with what we were talking about earlier, where A is B. And then they asked for the reverse. Is B A? The results? It worked. The AI is totally able to connect the dots when the question is clear and unambiguous. So what that's telling us is that as long as it's very clear when you're in the little village that you're trying to go to the big city, or the big city and the village, if it's worded straightforward, boom, you can get there. So what seemed like a curse might just be a case of us not asking a very clear question. This is a prompt engineering issue. Or it can be done in the trading set too, but then you would have to have in there about the same amount of references, kind of normalizing the amount of times that you talk about Ed Witten and the connections that it goes to with Taylor Swift and the connections she goes to. So what at first seems like it's an AI blind spot, the reversal curse, it's more just about understanding how the connections are actually made inside of these large language models when you have like trillions of parameters, and framing the question in a way where you give it the guidance it needs to not get lost. But now make sure that mouse cursor doesn't get lost. Help me get to my next goal, 9,000 subs. Thanks.